Given a graph G, a subgraph of G is another graph with the property that the vertices of the subgraph are also vertices of G, and the edges of the subgraph are also edges of the original graph. In other words, you get to subgraphs by deleting vertices and or edges from G. So we're going to say that a subgraph is spanning if it has the same vertex set as the larger graph, or we're going to say that a subgraph is induced if it has the following property. Given any two vertices in the subgraph, if there's an edge between them in the original graph, then we're requiring there to be an edge between them in the subgraph. The advantage of subgraphs, or induced subgraphs, is that they can be identified by their subset of vertices. So for any subset of vertices, the subgraph induced by S has S as its vertex set, and its edges consist of all unordered pairs of edges in G whose both endpoints are in S. So for example, we'll let G be the graph with vertices A, B, C, D, E, and edges going around in a cycle like this. Then I'm going to let K be the induced subgraph on the vertices B, D, and E. So that's vertices B, D, and E, and then the red edges from B to D and D to E. Now that graph is not spanning because it's missing vertex A and C. On the other hand, we're going to define H to be the subgraph consisting of every vertex, and then just the yellow edge from A to C, and the edges from B to D and D to E. Now H is spanning because we've included every vertex, but it is not induced because, for instance, we have vertices C and E in our set, and in the original graph there's an edge between them, but we did not include that edge in this subgraph. So a graph G is called a complete graph if for every pair of vertices we have an edge between them. And oftentimes for notation we'll let capital K sub n be the complete graph with vertex set given by the positive integers 1 through n. As can already be seen, the number of vertices in the complete graph on n vertices is n, but the number of edges turns out to be n times n minus 1 over 2. And that is because n times n minus 1 is the number of distinct ordered pairs where both coordinates are different, and we divide by 2 because our edges are unordered pairs. So for example, here's the complete graph on 1 vertex, the complete graph on 2 vertices, complete graph on 3 vertices, the complete graph on 4 vertices, and the complete graph on 5 vertices. So going back to subgraphs, a clique in a graph G is a subset such that the corresponding induced subgraph is a complete graph. So it's a subset of vertices where every pair of vertices in that set has an edge between them. The clique number is the size of the largest clique in your graph. Conversely, we're going to say a set is independent if the corresponding induced subgraph has no edges. So this would be a subset of vertices in your original graph so that no two of them have an edge between them at all. The independence number is going to be the size of the largest independent set. So here is an example of a graph. We've got 6 vertices arranged in a circle with edges between consecutive vertices, and then we add these 2 other edges. So I claim that the clique number for this graph is 3. To show it's at least 3, you have to show that there's a clique of size 3, and here's a clique of size 3. To show that you can't get anything larger, you have to prove that there's no clique of size 4, which means that in any set of size 4, you have to have a pair that aren't adjacent. So here I'm going to be taking advantage of some facts about the fact that we're having exactly 6 vertices, namely that you can actually group these vertices into pairs that have the property that the pairs are on opposite sides of the hexagon, and as we can see from the graph, those pairs do not have an edge between them. And so the point is, from each pair, if you're going to create a clique, from each pair you can only pick at most one of these endpoints, because once you include both, you have a non-edge. And since there are exactly 3 such pairs, that means it's not possible to create a clique of size 4, because by the time you've picked a fourth vertex, your fourth vertex has to be an opposite pair. On the other hand, I claim the independence number of this graph is 2. And so I see an independent set of size 2. We want to claim there's no independent set of size 3. And to point that out, we observe that consecutive vertices on the graph are connected by edges. So if you want an independent set of size 3, you have to pick 3 vertices on the outer boundary that are not consecutive. And it turns out for a hexagon, there's only 2 ways to do that, either BDF or ACE. And in both these cases, you can see that there's an edge. So there's no independent set of size 3, therefore the independence number is 2. All right, given a graph G, the complement of G is created by keeping the same vertices and then changing the definition of edge. So you have an edge in the complement if and only if you didn't have the edge in the original graph. So for instance, if we took the graph from the previous slide, its complement is created by taking non-adjacent pairs and making them adjacent. And so we see these opposite pairs now have edges, and then we've got a few other edges we have to add in. So one key fact is that the clique number of the complement is actually the independence number of the original graph and vice versa. And the reason why this is true is because a subset of vertices can only form a clique in the original graph, while if every pair of those vertices has an edge between them, but by definition of a complement, that means in the complement they don't have an edge between them. So you get a clique in the original graph if and only if you get an independent set in the complement graph. The other important part that's used to prove this result both directions is to note that if you take the complement of the complement, you have to get the original graph back.